Hello, my name is Jakub and by today's talk I would like to answer the question when high PV conversion efficiency is profitable and why low irradiance performance matters. I'm from Center for Advanced Photovoltaics at Czech Technical University in Prague and from Czech Academy of Science, and I did this work in collaboration with EPFL PV Lab in Switzerland. Our common goal here today is to help the environment, and one way to do it is to cover as much as possible of people's energy demand by PV technology. In our PV group, we follow a strategy based on three keywords: on oversizing, high efficiency, and half-sun optimization. To start with oversizing, we make a simple sketch of PV system containing PV modules on DC side, the inverter transforming to AC, and other components that are all included into a named BOS, balance of system. Economically, the total cost is divided to module cost and BOS cost. In conservative sizing, the ratio of DC to AC power is around 1. In case of oversizing, this ratio is considerably higher. Oversizing is described, for example, by white paper of German company SMA that says, with oversizing, the PV power plant's nominal power is achieved faster in the morning and the PV power plant remains connected to the grid longer in the evening. Adequate oversizing increases the profitability of a PV power plant. We also wanted to investigate the effect of oversizing by simulations in software PV-Sol. We look at a perfectly sunny day. We see that the power never reaches the limit of inverter for conservative sizing. When we go for oversizing value around 2, the power is clipped by the inverter limit. This clipping produces an oversizing loss that is economically as high as module cost. Oversizing produces also some gain that economically is as high as feed-in cost, which should be in the range of the total cost. How much the performance is affected by oversizing can be expressed by so-called performance ratio. That is the ratio between energy produced and nominal module power. Economic profitability will be then proportional to performance ratio divided by total cost. We already know that total cost is divided into BOS cost and module cost, and now we plug in also the factor of oversizing. Finally, the profitability is basically the performance ratio with additional dependence on oversizing and on ratio of BOS to module cost. We see that this ratio is effectively shifting the maximum of profitability to higher oversizing values, so that the oversizing is more profitable for higher relative BOS costs. Similar analysis can be done for a household system with the aim of maximum coverage of the consumption. Interestingly, the gains are now relatively low compared to previous case. The other difference is that economically gains are as high as the cost of electricity that the household is buying from grid. We quantify the losses and gains, and we evaluate financial balance for different ratios of module energy cost to grid energy cost, and we see that the higher the ratio between the cost of grid energy to the module energy, the more profitable is the oversizing. That was oversizing. It was interesting, but we do not really want to increase number of PV modules. We prefer to go for high efficiency. To evaluate economical profitability of high efficiency, we can use famous Martin Green's graph. The only problem is to add the cost of BOS, because I think that every time I switch to higher efficiency, I have to recalculate the cost of more powerful inverter. But if I remember the effect of oversizing and the effect of ratio of BOS over module cost, I see that with only small error, I get freedom for efficiency variations with fixed inverter. It means that I can modify the Martin Green's graph by adding BOS, and it is the oversizing that is allowing me to do it. Once I know I can use this method, I just have to make market survey of the module cost and of the BOS cost. But for BOS, I use average efficiency values to recalculate it to meter squares. And I also evaluate ratio of BOS over module cost for comparison. Now, how to evaluate all these data points? First of all, we care only about the best cases. Then we look for a general trend, and we know that it should be a curve starting at 0 and asymptotically approaches technological maximum that we assume as 26%. Mathematically, the curve is described by hyperbolic function with variable parameters c and g. Now, similarly to Martin Green, we plot the straight line expressing the cost of energy, and the most profitable is the tangent, and the touching point is the most profitable efficiency. If you do not believe me, you can calculate profitability and find the maximum. The idea to use this graphical analysis is that you can see how the touching point will move on the hyperbolic line when BOS will change, or the other way around, when BOS is constant and the module cost is changing. This happened between 2 years when we did this analysis on modules sold in Czechia. Between the 2 years, the most profitable module cost changed from 18% to 20%. If we continue by market analysis in other countries, we see that in different countries the touching point was at different level. And for example, in India it was at level of 21%. This is the way how we demonstrate graphically when high efficiency is profitable, and we see that it is for higher BOS over module cost ratio. But because the breaking news are coming from perovskite community, we want to apply this analysis to silicon perovskite tandem also. For that, we have to rely on some literature values of additional cost of perovskite layer and also make some guess about the maximum technological efficiency. Altogether, we arrive to quite rough numbers that when moving to tandem, the module cost increases twice and efficiency by 1/4. By doing so, we get green lines, and by looking closer, we see that green lines exceed the current best case expressed by red line, so that moving for tandem will be profitable. Interestingly, for Spain, showing the lowest BOS over module cost ratio, this is not the case, but it is again the case for the remaining countries like Brazil and India, confirming the trend that the higher the BOS over module cost, the higher is the silicon perovskite tandem profitability. So that was the high efficiency that was driven by either high BOS cost or low module cost. But I would like to be careful because not every time the high efficiency is relevant, and we want to show that it is relevant mainly at lower irradiations, let's say at half sun. Because if we agree that oversizing is beneficial, and if we make again simulations with capping the output power by limited inverter, we can see that most of the points lie on the left part of the graph, and on the right part there are not so many points that are not limited by inverter and for which the efficiency is still relevant. So for oversizing, the efficiency at higher irradiance is always less relevant. Question is, how to address this in technology? We investigate within our collaboration the technology of silicon heterojunction solar cells, and we already made a study with front contact layer by reducing its thickness and doping. At one sun, it is making problem, but at low irradiance the problem disappears. So the idea is to make contacts weaker while preserving their low light operation. It may have some obvious economic benefits like saving scarce materials, but we are more interested in more fundamental optical benefits that are also obvious because thinner layers have better transparency, and by analyzing this we found that thinner layers can improve electrical current by roughly 2% relatively. But there must be also an electrical benefit that we observed experimentally in past, that after some adjustments in technology, reducing efficiency at high irradiance, the efficiency at low irradiance increased by more than 5% relatively. And this is something that cannot be explained only optically. Therefore, we run some electrical simulations in Atlas Silvaco software, and we verified that weaker doping is not problem at low irradiance, but reproducing the positive electrical benefit was not yet possible. The only strong positive effect was observed for variation of TCO work function. But because this is currently our intensive work still in progress, this brings me to the end of my today's talk and to summary of most important conclusions. The higher BOS cost over module cost, the higher DC to AC oversizing is profitable. The higher grid energy cost over module energy cost, again, the higher oversizing is profitable. Oversizing allows adding BOS cost to Martin Green's graph and to evaluate profitability of high efficiency technologies. High efficiency is more profitable for higher BOS over module cost. And the higher BOS over module cost is driving the profitability also for tandem technology. For oversizing ratio 2, efficiency above half sun is less relevant. And when doing some non-standard optimizations, 5% relative increase was observed at low irradiance. Finally, I want to acknowledge the project and I want to thank you for your attention and give opportunity to questions.